Afternoon. Great, we'll make a start. So thank you everybody for joining us. Today is our third webinar in our series, and today we're going to be talking about lighting uniformity and is your airport apron meeting the ICAO standards. So before we get started, just a little bit of basic webinar protocol for those of you who may not use Zoom in a while. So everybody's muted. It's only us, the presenters, who can speak. So if you have any questions, please put them into the Q&A box. And we've also got the chat function enabled. So as Yuli mentioned, if you want to say hello to everyone, just make sure the blue box is to everyone and not just the panelists. Of course, we appreciate you saying hello to us, but say hello to everyone as well. But just a reminder, please pop your questions into the Q&A box. This just makes it a lot easier for us to answer questions as we go along. And at the end, it means we don't have to scroll through the chat to find them. After the webinar, there'll be a survey that pops up as you exit. We'd love to know how you think we've done today and anything you think we could improve on. So please fill that out. So we'll go into the main presentation, but first off, we're going to do introductions to our wonderful presenters. And for those of you who don't know us, a little bit about Midstream Lighting. And of course, we've got time at the end for questions. So during the main presentation, we'll talk about what is lighting uniformity and why does it matter. We'll talk about the ICAO Annex 14 compliance and their regulations and understanding uniformity ratios, how to measure uniformity on the apron, and of course, most importantly, how to achieve great lighting uniformity. So today we've got a wonderful selection of panelists. First up, we've got Yuli Grigg, one of the co-founders of Midstream Lighting and our commercial director. Yuli's been working on the aviation side of our business for over 15 years and has worked on hundreds of projects worldwide, so really is one of our aviation experts. We're also joined by Natasha Collins, our international sales manager. She works again on the aviation side of our business, and you have probably spoken to her before, and if you hadn't, you definitely should. And she also looks after our aviation partners. And Paolo, another one of the co-founders of Midstream Lighting, he's also our technical director and our resident expert on all things LED lighting. So for those of you who don't know us, we're Midstream Lighting. We're a high-mast LED lighting manufacturer and solutions provider, and we've been around since 2010, so we've been doing this for over 15 years now. We've completed over 150 airport projects worldwide and designed many more. And we are specialists, not generalists, and by that I mean we only design products and projects for our special sectors, so aviation being one of those, but we also work in the maritime and the sports sectors. And we don't just sell products, we offer a full turnkey solution. So that's everything from the lighting design right at the beginning of your project to manufacturing the products, delivery, consultation, and we also offer training and education to all of our customers. And that's why we're here today, to share our knowledge with you, to enable you to make the best decisions for your projects. So now I'm going to hand over to Natasha, who's going to take you through the main part of the presentation. Over to you.
Thanks, Sophie, and thanks for everyone for joining. We're really excited to have you for our webinar today on uniformity. So we've done 2 webinars so far, one on CCT and one on maintenance factor, and we chose those topics because we've been asked about them a lot. And unlike those topics, uniformity is typically a subject that actually gets overlooked because many people assume that uniformity has been considered and compliant when they're given a lighting design, but that's not always the case. And so when it's not done right, it can also cause real problems. So what is lighting uniformity? Lighting uniformity is how evenly light is distributed. So in terms of apron flood lighting, it means avoiding overly bright areas and also overly dark areas to make sure that there's consistent visibility for anybody who is working on an apron. We measure uniformity using a uniformity ratio, and that compares the average light to the minimum light levels. And we actually will go into how that's calculated a bit more later. So why is uniformity important and why does it matter? Uniformity is considered to be one of the most crucial aspects to ensure safety, to ensure compliance, and also efficiency. Uneven lighting or non-uniform lighting will cause problems for aircraft movement. It will cause problems for vehicles being operated on the apron, and also for any of the ground crew who are working on the apron. And this is why ICAO have such strict requirements when it comes to uniformity. It also impacts visibility for pilots, ground crew, and also surveillance systems. As you'll imagine, pilots rely on clear visibility on the apron to be able to operate safely. And having that inconsistent and non-uniform lighting, so areas of extreme light or darkness, is a hinder to safety. You can imagine if you're walking down the street in the dark and then there's an area of brightness and then you go into the darkness again, your eyes take time to adjust to this. And that's what we want to avoid for pilots. Same for surveillance cameras. So they depend on uniformity for clear imaging. And this is because dark patches create blind spots where hazards can also be missed. And just like our eyes, surveillance cameras take time to adjust and focus when there have been overly bright areas and dark spots. And so therefore hazards can be missed. So that is why ICAO has very strict requirements for uniformity. So as many of you will know, ICAO Annex 14 sets the global standards for apron floodlighting that ensures airports can operate safely. So the minimum ICAO lighting standards for aircraft require an average illuminance of 20 lux and a uniformity ratio of 4:1. At least a uniformity ratio of 4:1, or a 0.5 as it's presented as a decimal on your lighting design. So 4:1 is a quarter, and so it is represented as a decimal 0.5. So anything less than 0.5 uniformity means that you have an uncompliant stand. For other apron areas, there must be at least 50% of the lux levels of aircraft stands, but again, there's a minimum uniformity of a 4:1 ratio. So I'm now going to hand it over to Yuli, who will go into more detail about what that 4:1 ratio really means and also how it's calculated.
Yeah, thanks very much for that. I think indeed the 4:1 ratio is exactly what it is. It's sort of a relationship between two things. It's the relationship of the average and the minimum. And what we don't want is to have the difference being too great. We don't want something to be too bright and then have something too dark in the same area. Remember that in apron lighting, we're considering only the ratio of the average to minimum. However, there are other uniformity ratios that exist. So for example, when we work in sports lighting applications, we're quite interested in the ratio between the max and the min, so the maximum and the minimum, and that relationship is also very important. We're not interested in that in the apron lighting. In apron lighting, we're interested in the average illumination to the minimum. So here's an example when we thought this was important to just get that in the mind. A 4:1 ratio, which as Tash said, 0.25 is the decimal version of that, is basically having a 20 lux average, which is mandated by ICAO, means you should have at least a 5, well, you should have a 5 lux minimum, and that'll give you a 4:1 ratio. If you then drop that, or if the ratio drops to 5:1, that means you still have a 20 lux average, but now your minimum is only 4 lux. That means that you are out of compliance because it's now not 4:1, it's 5:1, and that's not allowed. So it's anything that's 4:1 or better. So 3.3:1 is better. It's 20 lux average with a 3:1 ratio of 6.6 minimum. So that is in compliance. That exceeds the minimum standards. So that's good. 5.1, of course, is not. And when we think about it in decimal place number, a 4:1 ratio is 0.25. So you have if you imagine a pizza with 4 slices, 1/4 of that is, one of the 4, 0.25. Likewise, if you have 5 slices, it's 5 is basically 1/5 of that, and that will be 5 to 1, or it'll be 0.2, which is not compliant. And then on the flip side, 3 to 1, 3 slices, and then if you take 1/3 of that, it's 0.3. So that is compliant. That's the way to think about it. And the reason why we say that is because the software only really Dialux only really prints it out as a decimal number. It doesn't do it as a fraction. So you have to have some mindset to be able to convert it. Now, when it comes to ratios, some airports that we've worked in the past have requested a higher ratio than 4 to 1. We've worked with some airports in South America that require a 2 to 1 ratio, and that's set by their local civil aviation authority, and that is mainly driven by security. So they want to have a very high uniformity for the cameras, and they want to have very high uniformity for the security and safety departments. So even though the ICAO recommendation is 4 to 1, some local authorities decide to increase it to 2 to 1, but it can never be less than or worse than 4 to 1. But of course, understanding that that is the requirement, we also have to think about how do we measure this on the apron? What is the physical process to understanding and taking those readings? And really, the way we do that is we have a lux meter, and we take a grid, which is inside our aircraft stand. We typically take, for the ease of counting, 15 measuring points for a small stand, code A to D. And for code E and F, we typically recommend 25 measuring points, evenly spread out across the size of the apron. And then we apply a ratio formula, which is basically we take all the average luminance. So we take the 15 points, we add them up and divide by 15. And then we divide that number by the minimum point, the lowest point that we've recorded inside that grid of those 15 points. And I think what's important to remember is that when you are recording this and checking for compliance, that we need to be doing this in the same points every year so that we have consistent data. And we also want to make sure that we're doing regular testing, that if there isn't degradation or changes in lux levels or uniformity, then we want to be able to capture that and see that as a trend. Now, maintenance is going to play an important role in this because there are many instances where you could have 1 or 2 luminaires that are damaged or out, either through a loose connection or debris or damage, or even manufacturing defect. And if you haven't identified them to be out, then when you take a reading, you could have some problems with uniformity or some with averages. So, consistent, regular maintenance is important. When we have poor uniformity, well, there are significant consequences for that. And it can be as diverse as fines, which are either fines which are put in place by the local civil aviation authority. There are instances where we have had an aircraft apron area decommissioned because of non-compliance. So in those instances, we've had the airlines issue a fine to the airport for not providing the pier that they had agreed to use because it was no longer available for usage until the lighting was rectified. So that's happened in the past. We know of instances where insurance policies were invalidated because they didn't meet the lighting requirements. And so any accidents or incidents that happened were no longer covered by insurance. And of course, generally, the accident risk is far reduced when you have a proper uniform system, which is in compliance. So just these are the things to think about when you're measuring and when you're maintaining your lighting system. So measuring things on the ground, and then the next step is to compare that to what you have in the design files, because I think it's very critical to remember that not every time, especially if you're not using experienced or well-reputed suppliers and manufacturers, that not everything in the lighting design is going to correspond to reality on the ground. But when you are looking at lighting design, here we have two snippets. And if you look on the one on the left, what we've actually demonstrated here is all of these points in the stand are measures of lux levels. So that's what the software has identified as all the different points. Now, it hasn't shown all the points. It's shown some of the points. Otherwise, there'd be too many to see. But this shows a selection of points on this apron stand. Now, in the bottom left, you see EAV. That shows you the average level. So the average of this stand is 73. Very high average. Very high average. It's something that is taken from a real case example. And then you have next to it a I just need to zoom in, E-min. So that's the minimum levels. Now, we probably can't identify that on this grid because it's somewhere hidden or is not shown amongst all the points, but it is in there. So the software said the lowest point in this square is 28 lux. The next one across is the Emax. That's showing the maximum level, the maximum points, 102. And that's typically highlighted with an underline on the square. And you can see that sort of in the middle there, 102. And then it gives us the U0, and that's the uniformity ratio as a decimal. So that's telling us it's the ratio of average to minimum is 0.387, which is better than 0.25. So therefore, it's good. It passes the compliance. It's well in the requirements. And then it shows an E-min, E-max, which is something I mentioned earlier, but we're not interested in this when it comes to compliance with ICAO standards.
Yeah, Yuli, let's say that the E-min, E-max is more of say, look on the aesthetics of what the apron was going to look like rather than a compliance parameter. You know, that the higher the E-min, E-max would be, the nicer it would look as well.
Okay, so what would be your view on that? Is that a nice looking apron?
Yeah, definitely, because we have an E-min, E-max, which is almost 0.3. And let's say the human eye starts to see a difference in light level with differences above twice of the lighting level. So below that value, you don't really see any difference. For you, it all looks the same. So you will notice that the front of the apron is slightly more lit, and then the lower part, the back part, is a little bit less, but it will look like a very smooth transition.
Yeah. And I think, if somebody thinks, why isn't it all exactly the same? Why isn't it just like a blanket of light on an aircraft stand? That's presumably because we can't have two different from both sides of the apron, right?
Well, having
we can't illuminate from the front and the back.
Yeah, having a uniformity of one is like a utopia. It's not effectively possible to have, because you're always going to have a little bit higher intensity closer to the light source. Let's say that when you go close or above 0.5, you start not to notice any sort of difference. So for you, it looks exactly the same. Above 0.5 uniformity, you get into like TV camera level of seeing the difference. Only instruments will see it, not you.
Right. Yeah. So so for human perception, anything above 0.5 uniformity is the same.
Yeah.
0.5, 0.6. Oh, good. Okay, good point. Yeah, so on the right-hand side of this page, what we're showing here is basically all of the aircraft stands, which are in a list. And in fact, the list probably will go further. And we're showing the different columns, and that's basically identifying the levels for each aircraft stand. So if we look at the U0 column, which is highlighted, these are all the uniformity values. And if we run our eye straight down, we're looking for anything which falls below 0.25. So 0.2, 0.24, anything like that is a failure. And we're checking to see if anything like that is here. So in this instance, it all passes. But that's something our designers will always be looking before they release a lighting project to ensure that nothing falls below that requirement. And I think Paolo wanted me to mention on this slide that the grid here says, for example, 19 by 19 or 19 by 11. That's how many measuring points the software calculates in each aircraft stand. Now, we don't show that and we don't measure against it. We only measure 15 or 25 points, but we do the 19 by 19 to check and catch the lowest point in the grid that we can, so that we always make sure that we catch the proper uniformity. I don't know if you want to add anything to that, Paolo.
No, I mean, this is just a good way to build up tolerance because, as you know, for example, uniformity is greatly affected by how consistent the installation is to what is done in theory on a lighting simulation. So if you allow for tolerance on it, even mistakes can be forgiven once it's installed. You always assure compliance.
Yeah. Okay. So on the next slide, what we're going to look at is the impact of safety operations. I think, Tash, you're going to be talking about this, aren't you?
Yeah. Yeah. So if we look beyond compliance and actually at the impact that uniformity has on the safety and operation of the apron, having uniform lighting essentially means preventing any dark patches or glare. So it makes it much easier to be able to detect any hazards or FOD on the apron. You can imagine that if there are any dark patches on the apron, hazards, FOD, anything that shouldn't be there is much harder to detect and is therefore then a safety issue. Good uniformity also means improved visual clarity for pilots and staff. For pilots, it enhances depth perception during taxiing and prevents any incorrect positioning when it comes to parking. Uniform lighting, therefore, actually reduces the risk of misjudging any distances or missing any obstacles. So it really does enhance the safety of the apron. When it comes to bad uniformity and the effect it has on pilots, firstly, it's slower taxiing, which causes delays and in turn increases fuel costs. So when there is poor uniformity, pilots are then likely to slow down, which leads to longer taxi times and then also higher fuel consumption too. Bad uniformity increases tiredness and fatigue, and therefore there are higher risk of errors. You can imagine after a long flight, especially these overnight flights, pilots come into park and they're incredibly tired, and having bad uniformity will only increase this. Glare issues also result in reduced visibility and reaction time. So excessive glare and particularly bright spots make it a lot harder for pilots to be able to see clearly and slow down their response time. Non-uniform lighting also reduces the effectiveness of CCTV and surveillance cameras. This is because cameras can't focus properly with inconsistent lighting. It only focuses either on the bright areas or the dark areas. So for CCTV, uniformity actually becomes more important than light levels. Paolo, you might want to expand on this point.
Yeah, because let's say that CCTV cameras, they do care much more about uniformity rather than pure lux level, as especially the newer generation ones. Their brightness level can adjust to even a very small amount of light and even show color. So I might have an apron or anyway a generic area which is lit to 2 lux in a perfectly uniform way. The camera will have the time adjust the brightness and you'll have perfect visibility. But if you suddenly have a space which is lit to 1,000 lux, but as an area which is 2,000 and an area which is a tenth of it, you will never be able to adjust the brightness of both areas are visible. You might actually have less visibility where you have more light than in the dark area, or a compromise when you see kind of badly both of them. So yeah, it is much more important to have uniform area rather than just a high average for this aspect.
Yeah, I also wanted to add something on this slide too, which I think is quite interesting. We had done some work on this earlier and some research, and when we talk about bad uniformity and bad lighting, when an aircraft is moving in the hours of darkness across a large apron area, it's feasible that due to tiredness and the ability to see depths properly, a pilot would naturally slow down his taxiing maneuver, especially if he's not very well, if he especially doesn't know particularly that airport very well. And so that delay, we know that, for example, at LAX, Los Angeles International, a delay costs about $107 per minute of delay. That includes fuel costs, operating costs, all the things that incorporate into it. So if you assume that even, 3-minute delay during taxi because of poor lighting for all the aircraft that land and take off at LAX, that's going to be something in the region of $20 million a year, because there are so many movements. I think there's let me just quickly check my data. I think there are 500 or 600,000 movements a year. If you take just, a third of that in the hours of darkness, then the cost would be somewhere near of 20 million a year. So it can have significant operational expenses to an airport if lighting is poor and not up to standard. So I just thought that was quite an interesting fact to share.
So let's look a little bit on how to achieve a good lighting uniformity. As with almost every aspect related to lighting, a good result starts with good planning. So we start to look at how to provide good lighting uniformity during a lighting design stage. Some aspects on this list are linked to where we're going to have freedom of placements on the mast. And when we're looking at a new project, when we're looking at a new project, we can make uniformity perfect every time. It becomes more challenging when you have fixed infrastructure, like a retrofit project. But one of the easiest way to achieve good uniformity is have a correct luminaire placement. This means having a correct interval of distance between the position of the eye masts. For example, an ideal position is having one mast every aircraft stand, which sometimes is done in airports in brand new constructions, even though it could be quite costly in terms of infrastructure and how many, actually even just the mast themselves. But the more dense the position of the luminaires is, and the more regular it is, the easier it is to achieve a regular uniformity between the various stands, and just generally a high uniformity on the apron. The use of correct optic, in this case, what we suggest is a well-developed asymmetric optic. When I mean well-developed, I mean something developed for this task. So with the right geometry in mind of a ratio between height and angles of asymmetry of a luminaire. By using a good asymmetric optic, achieving uniformity both on theory, so when working on the software, but also in practice, becomes much easier. When you have the right optic, you work with, say, a multi-layer approach. So you identify which way the luminaires have to aim, and you add luminaires to reach the light level. So basically, every luminaire distribution will add on top of each other until we reach the lux level, but the uniformity is given by the shape of the distribution. This means that if you lose a luminaire, for example, you're not going to have a decrease in uniformity. While if you try to achieve uniformity by using many symmetric beams, you're effectively lighting some parts of an apron exclusively with one or two luminaires. And you sort of try to compose this uniformity by composing a puzzle of light distributions. This is definitely not ideal. Also, every distribution is going to have its peak and its decrease, peak and decrease. So your light uniformity ratio might look good on paper, but might not look great on the field, actually. Unfortunately, sometimes this is not a choice. It's impossible due to existing infrastructure. So to reach extremely far away from high mast, you need to rely on symmetric optics. But we try to avoid it as much as possible. Another thing which is very linked to this same aspect is the optimal mounting height. The higher, the better, always is a rule when trying to light something uniformly. So a ratio between the size of the area and the height of our lighting point assures to be able to have to reach the furthest point in the area without having to either increase too much the tilt or increase too much the light in the part closer to the light source. So having a correct height will help achieve the uniformity, also use less energy, because by tilting you decrease efficiency, and also you keep the glare under control, because with lower tilt means that luminaires are flatter to the ground, and effectively its light intensity becomes smaller, lower to the observer, and also doesn't go as far out in the airfield. Minimizing obstructions. This is again something which easy to do on a greenfield, more difficult, more challenging to do on a retrofit project. But the biggest enemy of light is physical obstacles, because they create shadows. So in many airports, you will have, especially for the stands which are attached to a terminal, you will have fingers, you have bridges, you'll have little parts of the construction which stick out of the terminal itself. So understanding and taking that into consideration into a lighting design by adding, for example, the 3D models of it, will allow you to avoid going to install, and you did a simulation just based on a flat AutoCAD drawing. Then you realize that half of your luminaires are actually blocked by a building. So instead of having some light there, you have this massive black cube and black square on the ground. Of course, this obstruction, minimizing the obstructions, is mitigated by understanding where the obstructions are and using light source maybe on the opposite sides to contribute to a certain area, crossing beams. There are lots of ways to do it while doing the lighting design, but you need to take obstacles into account in order to be able to do so, or you will have big surprises.
And of course, we have a lot of practice with this parallel with maritime sector, right? Because of all the container stacks in ports, that becomes a real hindrance, because you have a port with no containers and the next day it's full of containers.
Yeah, exactly. That makes, having a physical object standing in the way makes all the difference. Now, that would go also for planes, but for example, the ICAO indication of the 20 lux is already taken into account that there will be a plane on the stand. And so the calculation is done on an empty apron, knowing that when there is a plane, the level on the ground will be lower.
So that's a good point, because we didn't cover this in the slides, but we are asked a lot whether the requirements for 20 lux and 0.25 uniformity must have the aircraft on the stand or clean and clear.
No, it has to be clean and clear, also because the moment you place an aircraft on the stand, you will have 100% some points which are even 0 lux if they are directly under the plane. So it would be physically impossible to reach the 0.25 uniformity. Let's say that maybe we didn't mention a lot the uniformity. We mentioned a lot the uniformity on the horizontal level, but an important aspect is the uniformity on the vertical plane, which is the, say, second requirement of ICAO. That uniformity on vertical level, so meaning not light falling onto the ground, but falling onto a vertical surface placed onto the apron, is actually meant to provide the lighting uniformly onto the body of the aircraft for ground operations. Actually, two things. One is to make sure that if you're pulling into an apron and there is a person, an obstacle which is tall, you see it in 3 dimensions, because there is light hitting the vertical surface, so for pilots, but mostly it's for ground crews. You're sure to have a 0.25 uniformity over the whole fuselage of the plane. If you didn't have this requirement, you could have perfect light on the ground, Then airplane comes in, and you only light the first 10 meters of the fuselage, and where you actually have to unload the baggage is pitch black. So this allows you to be able to work on all the parts of the airplane, whether it is for baggage, refueling, any sort of maintenance, even with the visual checks on the engines. That's where the uniformity on the vertical plane comes into play. Where were we after minimizing instruction? Yeah, well, lighting simulation, all these things fall within the realm of lighting simulation, which again, can't stress enough how important that is to do things in the right way, using the right inputs. And this is the only way to ensure that once something is installed, it's gonna look good, perform well, and be functional, is to have done your homework while doing the lighting simulation, account for whatever extra units you might be, because in the area has a lot of obstructions, and instead of trying to save 3 luminaires on a major international hub, you install those, then it's going to be a good result on the field. And then as of anything, regular maintenance, at least regular checks, which then could result in the need of maintenance, are the way to ensure that these results are long lasting. Because sometimes it might be as easy as a couple of breakers that tripped and you have a few luminaires out, very dark area, operator, the uniformity is low, even maybe you're still meeting your lux level requirements, but you're feeling the uniformity, operator distracted in a dark area, touches a part of the plane, and there's your 20 million damage that could have been avoided by a regular check of MCBs.
Thanks, Paolo. I think the main thing that really we want to conclude and get across from this webinar is that it's not enough to just have the 20 lux average on your apron. ICAO really sets out these strict requirements for the 4:1 ratio for a reason. So we want you to be able to check your lighting design and not assume that because a lighting design has been given to you that the requirements are met. As I mentioned at the beginning, it's one aspect that really can be easily overlooked, but it's one of the most important points to ensure that an apron is safe. Thanks, Sophie.
Wonderful. Thank you very much to our presenters. So we're going to questions now. We are running a little bit over, but we'll make this quick. We'll do a couple of questions in 5 minutes. So our first question, how do you evaluate from multi-apron stand? Who would like to answer that one?
I'll take on this. A multi-apron stand, so a Mars configuration, meaning we have an aircraft stand which can accommodate a large plane, or in the same surface you might accommodate 2 or more smaller planes, needs to be evaluated for all its possible combinations. So as a whole for the biggest plane, and then just the smaller areas which will take the smaller planes also have to be compliant by themselves. So you need to assure that a section of the apron of the stand is also compliant by itself. So you need to have uniformity, local light level as well. So you have to consider them as if we're not grouped together, all individually.
Okay, wonderful. We've got quite a few questions coming in. If you could pop them into the Q&A box, that would be wonderful. So I think along the same lines, how do you evaluate 3 stands that are next to each other? Do you evaluate each apart or all together?
They always have to be evaluated singularly, because you have to think that is what you're operating, that aircraft stand. Then there is a value which is actually comes from a different part of the normative, which is other apron areas. So basically a rule is that neighboring stands, like any neighboring areas, cannot be less than 50% of the one you're evaluating. But that's extremely difficult to happen on actual aircraft stands, but they always have to be evaluated individually. You cannot group them together, because you will have instances when you group 5 of them together, and you have, oh, I have a great lux level and great uniformity. But in reality, the central 2 or 3 would be a 10 lux average by themselves. So meaning when you actually operate that aircraft that's parked there, you want to have as good visibility of the rest. So always evaluate them individually.
Thank you. I think it's also worth just saying we do have a photometric guide, which is really good for how to test things. And we have done a previous webinar with Yuli as well around measuring lighting. And there's some great tips on there. So we'll definitely link to that in the email for those of you who'd like to know a bit more about that. So our next question, what would you consider is the maximum size for one grid to determine uniformity?
So the grid size that is used to evaluate uniformity, but also the lux average, we need to make a distinction. Onto the lighting simulations, when doing a project, you follow the rules which are set by like EN 13201, which they don't apply just for aircraft, but for any sort of area. They tell you how do you measure lighting in a certain area. So depending on its size, there's a formula which will give you as a result how many points by how many points you need to give a good enough result that is actually realistic. Often this is much more than what you will measure on site, because say if I have an aircraft stand and this normative will tell me I need 19 by 19 points, it means I'm spending the entire night measuring that. So in practice, I'm going to use less measuring points, like 25 or 15, so a regular grid of 5 by 5, and then I compare with what I have on the simulation. The results have to be within certain tolerance, and I will pass on those measuring points in practice. There's always a little bit of distinction between theory and practice. You know, you work a simulation in theory, but then what you can measure effectively in practice is not as precise because it would take too long, unless you use automated measuring systems, which are on the market. They drive around the apron with the car, and in that instance, they take so many measuring points that is actually you can get exactly the same results as your lighting simulations.
Sophie, can we just keep the questions going? Because I know we're running over time and we'll try and finish in the next 15 minutes, but there's some really good questions, which I think are excellent to try and answer them. So let's just keep them going.
Yeah, sure. So our next question, why do we need to do a lux level check if we have the lighting design confirming the uniformity?
Well, you always have to check that things are actually as in the theoretical simulation. That goes for the lux level as well as the uniformity, because what matters is what you actually have installed, not what the lighting simulation says, because you're going to see the consequences of the real life measurements. And also the Civil Aviation Authority is going to come and check those measurements. So you have to verify the project with real life data, but also that is what guarantees you are compliant and you can effectively operate the stand.
Which basically leads into another question here, which says, how is it possible to have different results in the field from the paper? And the answer can be as simple as that during installation, the aiming wasn't done exactly to how the simulation needed it to be done. So just bad aiming or bad angling could be a simple answer. Secondly, could be that the luminaires have degraded faster than expected due to their bad construction or some other reason, some damage. Or it could be the fact that the people that created the simulation, frankly, didn't put the correct data in. Or in some instances, we've seen cases where people have lied on their simulation. So if it's not a very trustworthy or experienced manufacturer, the suggestion is, verify, because it's not guaranteed that what they've proposed is actually what will happen in real life. We've seen that play out, as I mentioned, in Istanbul, where there were 11 manufacturers invited to the airport to do a mock-up, and only 3 of them were able to demonstrate that their practical lighting levels met the simulation. The other unfortunately, the other companies all failed to deliver the same results on the ground as they had on paper. So it's actually a very serious. It's actually a very serious thing.
Okay, thank you. Right. Thank you. We've got some awesome questions coming in. Just a reminder, please pop them into the Q&A box. So our next question. I have noticed that vertical calculation surfaces on the snips have been shared in the presentation. Are 110 degrees? Kindly clarify this, and are there any recommendation degrees for vertical surfaces?
Yeah, this is always an ongoing debate because, well, let's say start from on the simulation, it's at 110 degrees, but that's based on the position of the drawing itself. So 110 degrees is not an absolute value, it's just a direction on that specific apron, on that specific project based on that AutoCAD drawing. ICAO does not tell you what these relevant directions are. They like to leave it to the operators and sometimes the civil aviation authorities to define that. There are manuals for airport lighting which do get into the detail of specifying what the relevant directions are. And also EASA, so the European reception of the ICAO regulation will tell you what these planes are. Mostly, I mean, also the interpretation which I agree the most, which is the one which EASA will tell you that the relevant directions are the two perpendicular directions on the airplane fuselage parking positions. And this is what allows you to say that you're lighting both sides of the plane well with the uniformity of 0.25, which means that in the worst case scenario, no part of the fuselage will be lit at less than 5 lux, which means either the tail or the front of the plane. And that is effectively, I think, the most useful way to use vertical calculation. Other civil aviation authorities, which do not fall under, the European, the ones following European EASA, will only take one direction of vertical, which is actually parallel to the parking position of the plane, facing inwards. And that will represent the visibility of an obstacle looking out into the aircraft apron, which that has been done a lot. For example, in the UK, that is the most used type of interpretation. I believe it's a bit reductive, but I'm not a civil aviation authority, so I can make that change. My recommendation would be to have two relevant directions on the sides of the plane. That will ensure the best lighting possible for ground operations.
Wonderful.
Thanks. Paolo, one question coming in from Gabriel. He says uniformity is equal to minimum illuminance versus average illuminance, as opposed to average illuminance versus minimum illuminance. So the other way around.
Yeah, it's the same thing. Let's say that in America, they like to express this by the average over minimum. We express it as minimum over average. So that was the difference between saying 4:1 or 0.25. Just looking at the same data, just written in the other way around, but the end result is the same. Yeah, I agree. I rather express it in decimals.
What is the difference between ICAO and MOS 139? I'll just tackle that. I think MOS 139 is the Australian standards, and they're quite often exactly the same as the ICAO requirements. However, Paolo, do you remember the only difference in Australia was that for small airports, small aircraft, they had a different requirement, which was, I think, a 5 lux average and the different uniformity, or maybe the same uniformity.
But Australian,
do you recall from memory?
Yeah, the MOS 139 also goes into detail regarding the relevant directions on the vertical plane and follows the same path of EASA, of the European regulation. So in Australia, when doing vertical calculations, you must use the two relevant directions perpendicular of the fuselage in order to be compliant, which is, again, we believe the best interpretation. And yeah, they also have a lower light level specified for small airports, which is similar to the general aviation regulations that we have in the rest of the world, which is a 5 lux with 0.25 uniformity, which is quite low. But
yeah, but the uniformity is the same, right?
yeah, uniformity is the same.
Okay, our next question, what is the best grid to validate uniformity according to ICAO standards? With how many airports, how many points to evaluate an EF stand? 25, or in which positions should they be measured within the area of the size of an E and F airplane?
So as we touched this argument before, the ICAO does not tell you how to measure nor where to place the points. That is a task of lighting normatives that define the number of points. So again, the exact number of points needed for a uniformity calculation is given by a lighting normative, whatever the local relevant is. And it's a result of a formula taking into account the size of the area. For practical measurement, the minimum for an apron that size is 25 points. That is the minimum you need to evaluate if you actually have a good uniformity or not. It might be enough to show compliance. That depends on the aviation, the Civil Aviation Authority requirements. But let's say on a practical point of view, 25 points is the bare minimum you need to make sure that you have a decent uniformity. And the way you place the points, we're going to refer you to the to our guide on the website, because it's a bit lengthier process.
Brilliant, thank you. And there's part 2. How do you interpret measuring vertical uniformity in the relevant direction?
Well, this is, we just discussed about this. So the uniformity is calculated in the same way as the horizontal. So by taking into account the average lighting, minimum lighting, and measuring points, the relevant direction depends on the interpretation of the relevant normative in your country, whether it is single direction or 2 directions. And that also affects where the points are, because if you're looking at a double direction, I forgot to mention, the most common way to do it is by having, instead of a full grid on the apron, to have 2 lines facing outwards onto where the fuselage will sit. So you have a little bit less points to worry about. They're harder to reach in terms of lighting level, but easier to reach in terms of uniformity because your area is smaller.
Thank you very much, Paolo. Okay, I think this is going to have to be our last question. So we've got, would the process be different for a code C stand compared to a code F stand?
Same thing. The size doesn't matter. The methodology is identical. Just the number of points change according to the size.
Okay, well, it was a very quick answer, so we'll squeeze one.
Can you do a quad like the one about the taxi lanes?
Yes, of course. So do you usually illuminate taxi lanes on apron areas?
And just, I think it's taxi lanes as opposed to taxiways, Paolo.
Well, I mean, generally, the task of apron lighting stops at the end of the aircraft stand. So actually, that should be a hard stop. There are actually even many arguments that the lighting, if it surpasses the end of the stand, is actually a very bad thing because it reduces the visibility of in-ground lights and other visual aids. So we generally do not light taxi lanes or taxiways and try to avoid as much as possible to do so. But though there are instances when we've been asked to do so because there are no lights in ground on maybe some smaller or more outdated airports. So the added visibility of the lines on the ground from the apron lighting was seen as a benefit. So unless specifically asked for, we avoid lighting outside of the aircraft stand.
And what about interstand taxi lanes? So those are the little taxiways that are inside the aircraft apron, moving between stand to stand.
Oh yeah, no, those are fall within the area that it's lit. But I mean,
And would
they're
you
not
consider those to be? So they would be other apron areas, right? They wouldn't be aircraft stands because that's not for disembarking. So they would fall under the
other
other
apron
apron
yeah.
areas.
So 50% of the level
And
of the actual stand.
and is there uniformity requirement for other apron areas?
It's the same as the apron area, yeah. So always 0.25.
So that will be the answer.
Okay, wonderful. Right, that's all we've got time for today. We still have some other questions we haven't answered, but we will follow up with those. Apologies to anyone who was on our previous webinar. We still owe you some answers to those questions. So we're going to follow up to all of the many questions we've been asked on the last 3 webinars, because I'm sure you'll all find them interesting. So if anyone has got anything else that they haven't had the opportunity to ask, you can email either Yuli or Natasha. Their details are up on the screen right now. If we've got our next webinar in 2 weeks' time, where we'll be talking about how to specify the best solutions for airport apron lighting, and we hope you'll join us on that. So a huge thank you to you all. It's been wonderful. Thank you for your participation and all your questions. And a big thank you to our wonderful presenters today. Thank you, Paolo, Yuli, and Natasha. It's been great.
Thank
And
you.
we'll see you all soon.
Thanks very much. See you in the next one.
Bye-bye.
Thank you, everyone. I'll just leave this up on screen for a minute in case anyone wants to take down Natasha or Yuli's details. Thank you, everyone. See you again soon.